So today we're gonna start lecture 19, and we'll be talking about quantum entropy very briefly, maybe one slide, and then switch gears and talk about identical particles and the symmetrization postulate. All right, so this is the last postulate of quantum mechanics that remains. An important statement is that this last symmetrization postulate is not really a postulate because it could be derived using quantum field. So if you just don't know about quantum field theory, because you have to take it as a postulate. Otherwise, it's something you derive. All right. I want to say another thing. There's a lecture 20 I've squeezed in. We're going to go over statistics. Fermi-Dirac, Maxwell-Boltzmann, right? Statistics of identical particles. You've seen that in your undergrad class or not? How many of you guys have seen it? Okay, then I have to cover it. Because I was planning on not covering it, assuming that you've seen it before. All right, I'll have, it's good that I'm adding a whole lecture on that. How many of you guys have seen, know what a Dirac sea is, have seen how to make sense of a medal in quantum mechanics? Okay, wow. I'm not sure if I can cover that, but maybe I could squeeze in the homework. Thanks for the feedback. All right. So, review of lecture 18. We talked about two tools in quantum mechanics, the Schmidt decomposition and purification. They're intimately related. Here was the Schmidt decomposition said, if you have a pure bipartite state, psi AB, you can always write it in the following basis, in the following form. Sum over pi, I'm calling it lambda I, but I'm just writing it this way. To remember that because lambda i's are non-negative and sum over lambda I squared is equal to 1, you could always consider the probability distribution, right? That's what the probability distribution is. So I can write the square root of pi, right? Ket IA, ket EAIB, and these are orthonormal bases, orthonormal bases, right? Or A. The coefficients are called Schmidt coefficients, and we derive this, right? Good. Then we said one nice thing about the Schmidt decomposition is actually there is no analog of Schmidt decomposition for more than two particles, two systems, tripartite, fourpartite. If there exists, that's actually the origin of the fact that entanglement for more than bipartite is extremely hard, next to impossible. We had to talk about this yesterday. Now, given the density matrix, it's possible to introduce an auxiliary system, fiducial system, R, called reference, and find a pure state of psi AB such that psi AB reduces to rho A. Such a state is not unique. We're going to call it the purification of rho of A. And one trivial way you could prove this statement by construction, because you say they always exist. Here is one example, right? And yeah, in the language, I have not talked tensor. Next time I teach quantum mechanics, I'll squeeze in tensor notation because it's so convenient. All right, good. Yeah.
In the first definition, you said IAs are orthonormal states. But here you said bases.
Yeah. So whether or not it's a basis is the following statement. Am I writing rho I positive or rho I non-negative? It's a question of, rho I, lambda I or pi. Imagine one of the pi's is 0. In which case, you could write an orthonormal basis, but that term is not doing anything, it's dropped out. Right? The issue of whether it's a basis or not is a question of, are all of these guys non-zero? If all of these guys are non-zero, then it's a full basis, right? But if one of them is 0, right, then that term, that drops out. Good question. All right. We talked about Bell's inequality and how it ended local realism, at least in the scientific community. The news hasn't made it out. And the experiment was, the ideal experiment was Alice and Bob are performing measurements on qubits, right? And Charlie sends them qubits, right? Alice can choose to do 2 types of qubits, and she chooses it by coin flip. We call them Q and R. The results of the measurements are +1, -1. Similarly for Bob. Then we said local realism tells you that if the values of these measurements are predetermined, there must exist a probability for each configuration. We're going to call that P of little q, little r, little s, little t. Then just by basic addition and multiplication, you derive this inequality, right? This, all it assumed was that there are predetermined values associated to measurements. Then we said, let's do the calculation in quantum mechanics, replacing expectation values of coin flips with actual expectation values in states. So here was one particular suggestion: take the state to be this particular Bell state. Those are the choice of measurements, and I will try to have this as a homework problem for you guys to calculate that this is true. That in this state, what you obtain is 2 square root 2, which is larger than 2, so you can go do your measurement and experiment. And if you find anything larger than 2, that should be the end of local realism. And we said that it did happen, it keeps happening every day. Good. There are fancier and fancier versions of this. Any questions about the last lecture? All right. So now I'm going to take advantage of the fact that I already defined Schmidt decomposition to just define a quantity called quantum entropy. It's a fascinating quantity that plays a major role in our modern understanding of physics today. And it would not be an overstatement to say that in the future, people might know more about von Neumann entropy, might learn about von Neumann entropy before they learn about concepts like energy or some more seeming fundamental concepts of physics. So what is von Neumann entropy? I don't have time to give you the interpretation of it. You know, how many of you guys know what Shannon entropy is? Okay, so then this conversation remains at the level of analogy that, and a bunch of definitions that I cannot stress this enough. Shannon entropy and its interpretation was one of the most genius results of 20th century. The idea is as simple as this. If I have a statement, somebody tells me a sentence, right? It's cold outside. How much information does that sentence have? Give me a number, right? Shannon answered this question. And the answer to that question, I don't know how many of you guys know how he did this, but it's absolutely brilliant. He solved that problem. And on the way, he defined a master function called Shannon entropy. So the Shannon entropy is associated to a probability distribution. The input of it is a probability distribution. The output is a number. It's a positive number. This is the definition of it. Given a probability distribution P, H of P, is minus sum over I pi log pi. This is the amount of information you lack about something. When Shannon entropy is 0, you know everything. When Shannon entropy is large, there's a lot you do not know. Good?
I think I've heard something like this, but it was raised in terms of Shannon information. Is that equivalent?
People use all sorts of words for it, but that's just words. Right. So this takes values if I runs from 1 to b. Okay. This takes values between 0 and log d. So Shannon, if you wish, actually the answer to your question, I said when it's 0, you know everything. When it's log d, you know nothing. So you could define log d minus Shannon entropy to be the amount of information you know about the random variable. That's called negentropy. But those are, engineers love to invent words. All right, good. So that's what it is, right? This is a massive function. What we're going to do is we're going to define an analog of that in quantum mechanics. Remember that in quantum mechanics, if we do that, if we define quantum information, is way more fundamental than classical information. In classical information, information is associated to probability distribution and random variables. That's the lack of your because why are there probabilities in classical physics? Because I'm a terrible observer or experimentalist. In quantum mechanics, the amount of information associated with a density matrix, it could be purely fundamental. It's not a property of the observer or how bad they are. It's just foundational. You don't need to talk about poor measurements or bad approximation to have density matrices. We made that. That's why quantum information is a lot more physical than classical information. All right, so I will stop there. Otherwise, I won't get any. We've had complaints about the rows and p's being indistinguishable. So we are talking about indistinguishability in this lecture. So I'm going to use sigma for density matrix. So sigma, any density matrix could be diagonalized, and the eigenvalues of it are probabilities, right? So I'm going to write any sigma as sum over I pi ket I bra I. This is an orthonormal basis. Good. Von Neumann in 1935. Now this is a really fun fact. Von Neumann wrote the foundation of quantum mechanics before Shannon discovered his master function. Discovery of Shannon defining information, the birth of information theory is 1940 something, right? Good. Now it's actually interesting when Shannon wanted to give this a name, this function a name, he consulted physicists, right? And the physicist, there's a famous saying, I forget who told Shannon this. I think it's von Neumann. Von Neumann tells Shannon, I think that's correct, that we should call it entropy because in physics, nobody knows what entropy is, and we don't understand this either. Give it a bad name. And that's why it was called entropy. Turns out that, well, that was jokingly true. At the time, they didn't understand all the connections, but they knew it's very connected. This becomes, if you have learned about entropy in thermodynamics, this is the reason. This is a lot more fundamental than that. All right, anyway. So immediately, you could define von Neumann entropy, which is a generalization of Shannon entropy to quantum states, because we said density matrices are quantum probability distributions are classical states, quantum states are density matrices, right? So S of sigma, we define it to be minus trace of sigma log sigma. Now, plug in this form, and here you recover Shannon entropy. But why didn't I define it this way? because this is basis dependent, whereas this is basis independent. Good. Now, here's a fun exercise for you guys. What is a thermal state? What's a thermal state? No? What's it like? The density matrix of a thermal state? Yeah, E2 minus beta Hamiltonian divided, you have to normalize it. All right, plug this in the formula. You're going to discover an expression for entropy in terms of energy. Okay, so that's the first connection between entropy and energy. Now, this function is a continuous function. I want to say that. Anyway, you could use this analogy to derive the first law, second law, and third law of thermodynamics. Not only derive them, but generalize them instantly. I'll leave that for you guys to figure it out. All right, any questions about the definition? Every time you see an expression like this, first question you should ask is that, is log of sigma well defined? Right? What kind of number can I take the logarithm of unambiguously?
Dimensions.
Sorry?
Dimensions.
No. What kind of number can I just calculate the log of? Non-negative numbers. If my number is positive, log of it is well defined. If my number is negative, log of it is imaginary and actually not only imaginary, but it's also ill-defined. Right? Log of sigma is well defined because that's a probability distribution. Do not ever, this is another thing that you should know as a physicist. If somebody writes log of an operator, first statement is that they either don't know what you're talking about or that operator is positive. Yeah. Sorry, for this level, there are fancy, there are people who intentionally use that as notation, but yeah.
Is there like a quantum Fisher?
Oh yeah. Yeah, for sure. Relative entropy Fisher information. Spent a big part of my life studying those things. Yeah.
You said that you can derive the first and third laws, but like I thought the definition of entropy comes from the consequence of the second law. It seems sort of like
You don't need any of that. Quantum mechanics, what's beautiful is that people go on and on in class. It's so hard in classical physics to make sense of a lot of these concepts. In quantum mechanics, it's in your face. Yeah, but this is not a lecture about that. Yeah, maybe one day I'll teach a course on quantum information theory and physics, and then I'll go on rants about that. All right, questions? It's simple. The connection is simple enough that you could discover it in this weekend by yourself. It's simple enough. All right. Any questions? I just have a last slide about entropy, and we'll move on. What is the slide? It's the properties of entropy. Like its Shannon counterpart, von Neumann entropy is non-negative. It's equal to 0 if and only if the state is pure. Good? Which means that sigma could be written as ket psi bra psi. In d-dimensional Hilbert spaces, which is like I running from 1 to d, is always upper bounded by log of d. So by this definition, pure states, when you have a pure state, you know everything about it. When S of sigma is maximum log d, the state is maximal in X, which means that it could be written as identity over d. It is identity over d, it's not, it could be written as it. And this state, you know nothing about things. So now, remember the EPR pair I was talking about, the belt that I said Alice and Bob share an EP operator. Together they had a pure state. So when I said they know together they know everything, that was a rigorous statement. And when I said individually they know nothing, it's because the reduced density matrix of each of them is proportional to identity. Just also a rigorous statement. It's possible, just 1 second, it's possible to have a state where n parties share the state. These are very special states. If you group together any number of parties that's less than half of them, they know nothing. Any group more than half, they know everything. Those states exist in quantum mechanics. Yes, there was a question. Yeah.
The line actually, so on 2, S is less than 1, the line that equals what?
0, if and only if. Sorry, where are we reading?
No. So 2, the
D-dimensional whole space at S sigma is less equal to log D.
And then what's the next line? Equals what?
If and only if.
Equals.
Yeah, sorry, that's math notation. IFF is if and only if.
Okay.
Yeah. All right. Also, another thing, very important, is that for a pure bipartite state size, if you look at the reduced density matrix of one of them or the other one, they always have the same entry. What is the interpretation of it in terms of information? You could already interpret this. If Alice and me, we share an entangled state, my lack of knowledge is exactly the same amount of knowledge that she lacks. Whatever I know is exactly what she knows. There's some sort of symmetry in entangled states. That's obvious from Schmidt decomposition makes this obvious, right? When you can write any psi AB in this form, it's pretty obvious that if you calculate the reduced density matrix, it's going to be exactly the same. All right. This is a natural moment to pause because we are switching gears completely. Are there any questions about von Neumann entropy, Bell's inequality, entanglement, all of that? Not that I can answer all questions about entanglement. Yeah.
You said that different than Shannon. What is?
It's more fundamental. Let me give you a keyword and move on. Compression. There is something called compression, and that was the genius of Shannon. Shannon understood that how much information is there in a message is related to compression. So read about compression theorem. There's something called compression theorem. Yeah.
Saying that Alice and Bob have the same amount of information for a pure bipartite state.
Yeah.
Is that the same thing as saying that you can't distinguish between the two?
No. Not at all. We're gonna talk about that. Not at all.
Is it related?
No. Okay. No, not at all. A very, very good question. Because that's actually, I'm gonna use that as a segue. All right, any other questions? Good. So that was a beautiful question. All right. What are we going to talk about? We're going to talk about a bizarre phenomenon that's allowed in quantum mechanics and we observe in nature. We're going to interpret it. I'm going to motivate it, okay? But I'm just telling you in advance, this is a postulate of quantum mechanics. No, it's a postulate. I have to assume it, right? So there's no clean argument that gets there. I'm just going to motivate it, all right? The reason I can motivate it is that I can prove it if I talked about quantum fields here, and I actually proved it for a QFT that I'm taking this semester. But I'm just going to motivate it, right? It's a fact. It's a bizarre fact about nature. So what is it? is the following. Quantum mechanics allows for a weird phenomenon. In classical physics, if I have two particles or a bunch of particles, right? I can always keep track of them because I could measure this one, I could measure that one, and measuring this one will not interfere with measuring that one. I can put labels on them. This is particle 1, this is particle 2. I've been doing that, putting labels on these guys, right? This is system 1, this is system 2, right? And I just pretend that I can always do that. You might be able to, but you should, that's in classical physics, you definitely can, right? If you have two electrons that are moving along, you just observe their path or paint one of them blue, the other one green, or put like some sticky notes on either of them if we keep track of them. In quantum mechanics, so sorry, how do you keep track of it? You put sticky notes on them and you have to read the sticky notes to make sure what was 1, what was 2. In quantum mechanics, reading things, that assumes that these labels, sticky notes that you stick on them, are real. They move along, they exist when you don't measure it. In quantum mechanics, there is no such a thing. Everything must be measured, and you cannot assume the existence of predetermined labels. Right? We said that. All right, so let's make this a little bit dramatic. Take two electrons coming in. So as long as I'm watching both of them, this is like some, let's say, time direction or some path. As long as I'm watching them, I know where they are. But then I close my eyes for a bit, and then I reopen my eyes. E1 was here, electron 1 was here, electron 2 was here. I see these two coming out. When I was now watching, if it was classical physics, I knew by equations of motion that how they were evolving. If they were evolving in straight lines, they were evolving in straight lines. So I knew what is 1, it remained 1, what was 2 remained 2. But quantum mechanics says they don't have to do that. There is no such a thing as particle evolving on a straight line. This guy could do this, they could swap, or they could continue. Those are both allowed operations, and there's an amplitude associated with it. So if the initial ket that you start with was alpha 1, ket alpha 1 kills alpha 2, and this was like particle 1, particle 2, there isn't, if they don't, sorry. This is when you did not swap, and this is when you swap. There's no way for you to know by looking at here, this is in between, you close your eyes. There's no way for you to know whether they went straight or they swapped. But it's worse than that. There is no reality to what happened. It's not like they went straight or they swapped. It's a meaningless statement to ask what happened if you are not observing it. So there's no way of distinguishing alpha 1 and alpha 2, alpha 1, alpha 2 from alpha 2, alpha 1. Or as a matter of fact, there's no way of distinguishing any superposition of it. Right? What is the solution? Can you guess? If you just think abstractly in quantum mechanics, what is the solution to this? What do you expect to happen? There has to exist an observable, the same that plays the role of labels. And that observable, you should be able to measure and understand whether they are the same particles or they swap. But before doing that measurement, there's no way for you to know. Good. Those are the rules of quantum mechanics. So we're going to talk about that. Yeah.
We restrict ourselves to one dimension, because there's no exchange that we can say there's also for one level.
Very good question. So you said there's a particle on the left and there's a particle on the right. What does that mean? It means that you measured their position, right? So you could simultaneously measure their position. Yeah. So one you were not watching, how do you know that particle on the left stayed in the left and didn't just jump to the right and come back, came back or something?
There a physical process that corresponds to jumping. They can't switch.
There's an amplitude. There's an amplitude. You know, remember double slit experiment, half intervals? Anything is allowed. There's an amplitude associated to all of these guys. Yeah.
Given that like the time evolution of a quantum state is like maybe if not maybe a known thing is the wrong way to call it, but it's given. It's
Yeah.
not
Oh, that's
like-
correct. Okay, yeah.
Like if you have two wave packets, them doing that
Yeah.
is like a different time evolution than them doing this.
That's right.
And
You're brainwashed by realism. Doing this or doing that assumes that when you were not watching, they either did this or they did that. But when you're not watching, either of that happened.
well, yeah, I guess the literal like location of the particles wouldn't move through this space. But the wave function
There exists
moves.
there exists no calculation. Well, okay, sorry. The answer to your question is that when you were not watching, oh sorry, you said finish your thoughts. Sorry.
The wave function evolves according to a known rule. And it seems to me like in these two different paths, the wave
Good.
functions would evolve in two different
Very good,
ways.
very good. Awesome. That's a very good question. So I'm just gonna give you this answer. Remember the double slit experiment? Right? When I was not watching, I was sending a particle here, getting something here, I was sending here, I was getting something here, and when I was not watching, I was getting something like this. That is adding up waves, right? But what I'm saying is that there is no way to know. It's a nonsensical statement to say, when you saw an event here, it was this particle that hit there and not this one. Yeah, the waves add up, sure. But it doesn't, unless you measure all along, there's no way of saying that, oh, this particle came and reached here. And it wasn't this one that did that.
So like they become they mix together.
The sharp statement is that there is no way for you to distinguish between alpha 2 alpha 1, alpha 1 alpha 2, or C1 alpha 1 alpha 2 plus C2 alpha 1. Unless you do a measure. Good. But you could do a measure. We're going to describe that. It's a legit measurement. This is true for identical particles, right? What do I mean by that? Can you tell? Like for example, yeah.
Like they have properties.
Exactly.
They have physical properties that
They have
are unique.
other they have other physical properties that could be simultaneously measured as the position. That's the point. Right? For example, one of them has larger mass than the other one. Measuring the mass of the particle commutes with measuring its position. So that's okay. You could label them with their masses. But when you say identical particles, it means that all their other properties are exactly the same. Now we're just talking wave functions in the space or momentum. Good. It takes a while for it to click. But it's a consequence of quantum mechanics. There's no choice. All right. I said all of this. So what is the observable? How do you distinguish the two? Do you have a guess? The observable is swap, right? It acts on K prime, K double prime. Say these are the eigenkets of whatever basis you had, and it swaps them. Sometimes called permutation. It's called permutation because once you have multiple, it's more natural. Is this a unitary? Is this self-adjoint? Well, think about that. This is an observer. Swapping 1 and 2 is the same as swapping 2 and 1. Swapping 1 and 2 and its inverse are also the same. And they all square to 1. If you swap twice, you're backwards. Sorry. Good. So what is the measurement you do? It's an overlap measurement. You take two particles, right? There was some wave function here. You apply a gate, which is literally swapping the two, and you look at the overlap of this and this. So you measure this swap. Side P1, 2. It is a gate. If I have an observable A acting on system 1, A1, let's say these are the eigenkets of it. A1 acting on A prime, A double prime gives you A prime, A prime, A double prime. There's an observable A2. These are identical particles, so I can talk about the same observable acting on A2. That gives me A double prime. You see that if I sandwich A1 by two swap operators, that becomes A2. So that's very intuitive. If I have two particles, let me draw a picture for that equation. I have an operation A1 that I only do to the first one, right? Let's call it A. This is 1 and 2. I'm going to swap them, and then I'm going to swap them back. Pull the lines. This is equal to this. This is that equation. If you swap, apply something, swap back, that's like applying to the other guy. These are called tensor diagrams. They are incredibly useful. You could write a lot of equations this way. Okay. So it's an observable. Does it have eigenkets and eigenvalues? Its eigenvalues are +1, -1. Why? Because it squares to 1. P1 squared is equal to 1, right? Therefore, its eigenvalues must be +1 or -1. Is that clear? Good. Because it's the Hermitian operator, its eigenvalues are real. So it's a real number that scores to 1. What is that? +1 or -1? Good. So what are the eigenkets associated to +1 and -1? Here's the eigenket associated to +1. I'm gonna denote it this way. Notice the notation is kind of funky, but it's standard. And this is, so you could check this explicitly. The eigenket associated the eigenvalue 1 is the swap symmetric state. Is this one. When I add the K prime, K double prime with the swap, that's clearly swap symmetric. The -1 corresponds to swap asymmetric. I just subtract that. If we check explicitly, this is the eigenket associated to -1. All right. So, yeah. The double primes. Swap. Now, where?
The right equation. Plus or minus.
This one here?
Yeah.
I swapped them. Oh, this is you're asking if this is prime? That's the prime. Yes, this is the prime. Sorry. What was the question?
Yeah, if they're small.
Yeah. Sorry. Thank you.
first A prime, A double prime, A double prime.
No. This equation,
Okay, great.
let me write them in red so that you see these are actually it's helpful to write them this way. That's why we have color. Then I'm gonna write this. This one. Good. All right. Yeah.
And then since it's a physical swap, why don't we consider unity?
I'm not teaching quantum field theory. I cannot tell you why. But otherwise, I could. That's an allowed state. Actually, let me just say it this way. That's an allowed state. When we go out to nature, we could ask, we could look at our fundamental particle, electron, I don't know, different atoms, right? Silver atoms. We could ask, what do we get when we swap? This is an empirical observation. It's shocking. All the particles that we find in nature are either always symmetrized or always anti-symmetrized. We never find anything that you said. It's just a fact about nature that I cannot explain in this class. It's a consequence of relativity, but we don't know that. Okay? It's just a fact. It is part of the postulate. When I write the postulate, I'm gonna say this. When people discovered this predates quantum field theory. So this was taken as one of the axioms of postulates of quantum mechanics. By the way, there's a little caveat to this. This is true because the space is three-dimensional, and then there's dimension of time is one. This statement is true if the universe, now, we look around in nature, and nature's three-dimension space, right? And we see this. When we derive this in quantum field theory, we realize that, oh, if space dimension was anything larger than 3, 4, 5, 6, all of that, this holds. Dimension 2 is exceptional. That's our route to quantum. We'll come back to that. So 2 is a very, very exceptional where what you said can exist is allowed by relativity, and it was predicted and it was observed. But right. Okay, good. Any questions about this? So this is an empirical fact that the law discloses. All right. There is some sanity check. There was a question of Hamiltonian that came up. What is the Hamiltonian of two identical particles in quantum mechanics? Is P1 squared over 2m, P2 squared over 2m plus their potential, which is x1 minus x2. If there are some external potentials, they look like this. You see, obviously, this is swap symmetric. Right? And you see, obviously, if the masses were not the same, it wouldn't have been swap symmetric, right? Good. So the fact that it's swap symmetric, it means that the statement that I said here makes sense. Because if the Hamiltonian was not so, when the Hamiltonian is swap symmetric, a symmetrized state remains symmetrized for all times. An anti-symmetrized state remains anti-symmetrized for all times, right? If the Hamiltonian was not swap symmetric, that was nonsensical state. And you can clearly see for the Hamiltonian to be swap symmetric, to stand the chance, the masses should be the same. So we're talking identical particles. By the way, you probably noticed something funny is going on here. We're treating mass as something in quantum mechanics at this level as something you don't measure, which is a label. It's those sticky notes. Good. Any questions about this? It's very atypical of me to include a lot of references to experiments, but this lecture, last lecture I did, this lecture I'll do the same for a very good reason. We'll see. All right. When we choose particles, we associate physical properties to them, such as mass, spin, blah, blah, blah. One such property must be the following. Is it an eigenket of swap operator? And if it is, what is the eigenvalue? We said that it's either symmetrized or anti-symmetrized. So is it +1 or -1? This is part of the description of the particle. You have to tell me, is it +1 when I swap? If I have two of such particles and I swap them, do I get +1 or -1? To describe that, if you get +1, you say the particle is a boson. That's a name. If you get -1, you say it's a fermion. This is a purely quantum mechanical concept. It does not exist in classical physics. If there was something else, if it was neither symmetric or antisymmetric, like in 2 dimensions, as I'm going to say, then you would have particles that are neither bosons nor fermions. They have a name. You have heard it. What is it? Anion. We're going to get there. So when people talk about anions, it means that they're talking about eigenkets of the particles that as part of their description, I have to tell you what happens when I swap them. And when you swap them, you neither get back the initial wave function or -1 of it, you get something else. So now this fact that I said translates, the postulate translates to this. In nature, in 3 dimensions, when we go out there and observe particles, all particles are either bosons or fermions. There's nothing else. All right? All right, by now, we have talked about only 2. Is that my next slide? No, it's not my next slide. Sorry. If you have a wave function that's not symmetrized, you could define a symmetrizer and anti-symmetrizer in the following way. So just tricks, right? So you could add your swap operator +1. This symmetrizes it. You take an anti-symmetrizer. That's what you get. Okay, a question. Is this operator self-adjoint? Is this an observable? How would you check? Take the dagger. Okay, what's the dagger of identity? Identity. What's the dagger of the second one? P1, 2. I said it is an observable. I drew it as a gate. So yes, it is an observable. All right. Okay, so this operator is equal to its dagger. What is the square of it? If you take a wave function, you symmetrize it and symmetrize it again. What is that operation? It's like symmetrizing once, because once you symmetrize, the second one is trivial. So the operator squares to itself and is self-adjoint. What is such an operator? We gave it a name. Projection. These are projections. Well, that's the symmetrizer argues the projection. The anti-symmetrizer, by the same logic, is produces a projection. Good? Alrighty. This generalizes to multiple particles. n particles. If I have n particles, I can talk about Pij that swaps I and j particle. As usual, if I swap I and j again, I get identity. But notice that swapping ij and swapping kl need not commute. Can you see that? Here. Is that clear? Take 1, 2, 3. Swap these two, right? It becomes 2, 1. Then swap these two, 2, 3, 1. Right? You get this. You could just, I have to draw a lot of things, but you could check for yourself and they do not commute. All right? Good. When you take 3 particles, there are 6 permutations, 6 configurations. I've listed them all here. There are 2 types of such permutations. The ones that by going from this to any of these guys, you can get by swapping a number of times, right? You either get to them after an even number of swaps or an odd number of swaps, right? Those are 2 options. Keep that in mind. For example, this state is related to this by an even number of swaps, whereas this state and this state are separated by an odd number of swaps. Good? Now, there are states in nature, there are states that you could write down which are totally symmetric or totally anti-symmetric. Any Pij you pick, you swap them, you're gonna get, for the totally symmetric one, you're gonna get back your state. And if you swap for the totally anti-symmetric, you always pick up a minus. So when you have a totally anti-symmetric one, all the number of swaps give you a minus sign, even number of swaps give you a plus sign. Right? That's why I distinguish between. All right. So here's for 3 particles. Here's the total number of swap, totally symmetric and totally anti-symmetric eigenvalues. Eigenkets. They're simultaneous eigenkets of P1, P2, P12, P23, and P13. All right. There are 6 vectors, but for 3 particles, these are the only ones we see in nature. In nature, when we look out and look at the identical particles, when we put together 3 of them, we only get either the wave functions that come out are totally symmetric or totally anti-symmetric. No other options. One case is boson, the other one fermion. A bunch of comments. Notice that this is a 6-dimensional space. So I just showed you a 2-dimensional subspace of it, total symmetric and total anti-symmetric. There's another 4-dimensional subspace that are neither totally symmetric nor totally anti-symmetric. Right? Example. K prime, K double prime, sorry, plus K prime, K triple prime, K double prime is neither totally symmetric nor totally anti-symmetric. Good? Yeah.
Slide above, said those states are the only states that you find in nature.
That are seen in nature.
But could you artificially create ones that are not?
What does it mean to say that those are the only ones that are seen in nature? Whatever we do is part of nature. I didn't say, yeah. We're a part of nature, right? If I can do something in the lab and I can create the state, I say it's found in nature. So when I say it's not found in nature, yeah, but you know why? because whatever Hamiltonian I engineer is going to be symmetric, permutation symmetric. That was part of the concept of the thing. It doesn't matter if some natural process does it or I do it. It still must be the same. The theory doesn't allow for anything else. Yeah, you cannot, in your lab, you cannot violate laws of nature. It would have been cool, but. All right. Now, pick the antisymmetric case, fermions. One thing that you notice is that it means that if you have a bunch of fermions, 3 fermions, it's impossible for any pair of them to be in the same state. Right? Because under swap, it has to become minus itself, which is equal to itself. Therefore, the ket has to be 0. 2 fermions cannot occupy the same state. Fermi exclusion principle. Fermions are antisocial. Bosons are exactly the opposite in a sense. The extreme case is when they all pile up on top of each other on the same state. That has a name. We see that in experiments. It's called Bose-Einstein condensate. All right, I have to speed up. But 2 bosons can sit in the same state. For example, if you take a tripartite state of 2 bosons, you can put them the same, and symmetrizing it, you get this state. You could check that in your, and cover, you can check that after class and find my typos. And this becomes 1 over square root 3. That's where it comes from, square root of 2 factorial over 3 factorial. This is just a, this idea generalizes. If you have n bosons, so here are n bosons. So you have states k1 to kn, and there are a total number of n factorial permutations. If ki repeats ni number of times, the coefficient that sits out there is here. That's binomials. Like you could figure that out. I'm going to use this in the next lecture, hopefully, because now I'm doing another lecture on this to derive the statistics. All right. All right. Symmetrization postulate. This is a postulate of quantum mechanics. The wave function of a system of identical particles is either totally symmetric, in which case we call that particle boson, or totally antisymmetric, we call it fermion, under the exchange of any pair of particles. This is a principle of quantum mechanics. There is something unsettling about this. Well, not about this, but something else. I'm going to say in a second. So far, you've seen 2 observables, two observables that have absolutely no classical analogs. So what are the observables you've seen? Position, momentum, they have classical analogs. This swap operator and the fact that the eigenvalues plus minus 1 is part of the description of the particle, you have to say this particle is a boson or fermion. That is something purely quantum mechanical, right? Let's give that the name. Let's call it statistics. I haven't told you why, but next lecture will become clear. So you have to describe the particles. What's the statistics? Is it boson or fermion? What's the other quantum observable I explained to you? I showed you in actually the first few lectures that has absolutely no classical analogs. Spin, right? Those are the unique 2 observables you know that are purely quantum mechanical. They're not coming from something classical. Are they related? Anyone? Turns out, if you just go out in nature and ask Mother Nature, we find this striking, bizarre empirical fact. First of all, spin always comes as either half integer or integer. That's just a fact. All right? And particles are either fermions and bosons. And we observe that fermions always have half integer spin, bosons always have integer spin. End of the story. That's all we see. That's just a fact. This is actually true in all dimensions. This goes with the idea of spin statistics connection. It's a mysterious thing in quantum mechanics, but as usual, we prove it in quantum field theory. So this was derived in quantum field theory. It's unsettling about quantum mechanics. It's just an observation, but we prove this in quantum field theory. One of the successes of quantum field theory is that, yeah.
Is that the like half integer versus integer thing? I suppose this has to do with the derivation. Like fundamental, or if we defined the like sort of base unit differently, it would become even versus
It's fundamental. It's fundamental. Absolutely fundamental. Yeah.
It's just
Observational fact, yes. That's what I'm saying. If you do not know about quantum field theory, which assume that what we're discussing in this course, it's an observational fact, it's an empirical fact. But in quantum field theory, we have discovered quantum field theory since, and we prove this. So quantum field theory says the following. It derives this. It says there must be spin for particles. It must be either half integer or integer. There must be symmetry, exchange symmetry, bosons and fermions, and they must be related in this way. These are all successes of quantum field theory.
Yeah. Does quantum mechanics say anything about which type have mass?
There's no relation. The mass is completely different. All right. So I have about 7 minutes or so. Let me pause here and ask for questions. The rest, I'm going to talk about 2 dimensions and topological quantum computing. All right, any questions? Yeah.
Is K here just a dummy variable, or is it related with all cases?
A K is just a dummy variable, but you could think of these as particles moving with some momentum. Thanks for asking. So let me, before doing this, how do you're an experimentalist, how do you achieve swap? How do you build swap? Tell me how you do it. What is swap? So here's a slab in your lab. There's a particle sitting here. There's a particle sitting here. How do you build swap? Yes. Yes. Rotation. You take this guy, go around this by 2 pi. You solve it. That's not what I said. You go around by pi, actually. But the swap is you go around, you bring this guy here. Right. That's what. Then you shift both of them this way. The reason I said go around 2 pi is there's a reason for that. I didn't realize that. I'm not talking quantum field theory. All right, good. So let me do pi. All of these are pi's. All right. And this is like this. These slides could be my QFT slides, but all right. Good. Oops. Whoa, what did it? All right. That's how you do it. So you rotate. You rotate. Assuming translation symmetry, you just rotate by pi. So the observable is just rotation, followed by translation. And you apply this observable, rotation by pi, and then on your state, and take the overlap of it with before rotation, right? So let me draw this picture. Here are your 2 particles. Here's time. And here are your final 2 particles. So this is what you do. Good? All right. In 2 dimensions, you could rotate. In 1-dimensional space, you cannot rotate. Right? There's absolutely no symmetry made in 1 + 1 dimensions. That should be clear. Right? And when I draw this like this, I use the fact that the space is 2 + 1 dimensional. Right? You can see already, if I keep doing this, what am I doing? I'm tying knots. I might end up with a knot that I cannot untie. Right? I'm just tangling these things up. All right. A funny fact for you guys to think about. In 3-dimensional space, you could tie a knot. In higher dimensional spaces, you cannot tie a knot. If you pull things, everything goes through each other. Think about that. All right. If the fact that weird things happen, anyons can exist in 2 + 1 dimensions and not higher is related to that fact. All right, but let me just come back to Earth. This, as an observable, the expectation values are either +1 or -1. This is related to symmetrized versus anti-symmetrized wave functions, right? If they're symmetrized, I apply this 2 pi rotation translation. I get expectation value 1 or it become -1. Is that clear? Now, when I'm talking 2 dimensions, let's for a second, these pictures are really 2-dimensional. Let's for a second imagine that, oh, sorry, this 2 is annoying. Damn. Well, let me get rid of this. I'll say. Yeah, actually, that was good. That was good. Oh, that was good. All right. After pi rotation, let's imagine I get a phase. Right. So I'm doing this to a pair, and I'm getting a phase. When the phase is pi, that is fermion. When the phase is 2 pi, that's a boson. Let's define a variable S, which is this phase I get. The spin statistics theorem tells you that this variable is spin. That's the observation that we had. I called the spin statistics theorem, connection. Tells you that this variable is the same as spin, because when this variable is half integer, this is 2k + 1 pi. So this comes as a minus sign. When it's integer, this comes at an integer of 2 pi, and you get +1. Good? So this is a generalization of bosons and fermions. When it's anything but any generic theta, we're going to call it an anion. We're going to call it an abelian anion. 1982, a guy called Frank Wilczek realized that this is allowed. Actually, it was known that this is allowed, but he studied this. Frank Wilczek is going to be here next Wednesday at 6 p.m. He's giving a talk. He won a Nobel Prize, not for this work, for another work. So the guy is prolific, and you have to register to go see the talk. All right. Sorry, as presidential lecture. Yeah. Yeah, absolutely have to reserve this. They might be full. Yeah.
I did it like right.
All right. Okay, so Frank is going to be here, but let me just move on because I'm running out of time. All right. So in 2 dimensions, I've explained why, but there's the possibility of having these thetas, particles that show this theta, and they're called abelian anions. All right. So do they exist? Abelian anions exist. They were seen in 2020. Is this June or July? Oh, I think July. A group in École Normale Supérieure Paris saw it, and a group in 2020, another group saw it. You might recognize this name, Mike Manfra. So it was here at Purdue. And they saw this. As they swapped them, they saw an anionic phase with theta 2 pi over 3. So Purdue claims to be the first group in the world that saw abelian anions, actually. That's a fact. All right. I just have 2 slides on non-abelian anions. For those of you guys who are interested. 1988, forward, or however you pronounce that, he realized that there can be non-abelian anyons in 2+1 dimensions. I haven't told you what non-abelian anyons are. I'll tell you in a second. 1991, Moore, Reed, and Xiaogang Wen, they realized that non-abelian anyons could be realized in a physics experiment that would be called fractional quantum Hall effect. Right? You see how fast it moves. Early 2000, Alexei Kitaev, pure genius, he discovered that non-abelian anyons can be used to build qubits that are resilient to noise. This is the route to quantum computing. I can explain that in 2 minutes, actually. Why? It's absolutely brilliant, right? So this is the history of it. As usual, I have to draw these pictures. So what is a non-abelian anion? I don't have time to teach this or explain it, but what it is that the state of two particles is described by a wave function. In abelian anyons, when we're swapping them, we're picking up a phase, a complex number. Non-abelian anyons are these systems that when you swap them, a matrix acts on it. Right? I have not explained why or how, but that's what it is. The wave function is described as a vector with some internal mysterious labels that when you swap things, a matrix acts. Now, what you could do in topological quantum computing is prepare a bunch of these guys, and your logical gates are these matrices. You keep swapping them, you build a quantum computer by braiding these lines. Just rotate them, move them. That's what your topological quantum computer is. Now, let me tell you why this is brilliant. So if I want to apply a matrix, that is my gate, I'm going to prepare an electron there and an electron here, right? Actually, let me first do it next to each other. When I want to do a gate here, I want to do something to them. What is hard is that noise is going to appear. Noise is going to mess up things. But the genius is this: noise is local. There might be some crap going on here because these degrees of freedom are happening here, right? But when you separate these two guys by long distances and you just rotate this or swap them in space in large amounts, it will take a conspiracy of noise to ruin your data because noise is local. If you look at the measured noise here, noise there, there's no correlation. The further you go, the less the correlation is. So these qubits are resilient to noise for that reason. You could just like prepare them really far away and just rotate them. Another way of saying this is that the degree of freedom that we're looking at is absolutely non-local, it's topological, it's protected. That's the origin of the word topological. I'm out of time, I'm going to stop here. Are there any questions? Yeah. It's understood that noise correlation length decays to zero pretty fast. Correlation length is very short. Quantum noise. Depends on your temperature, depends on your environment. But the thing is, you could macroscopically separate these guys, right? That's what Microsoft is trying to do, by the way. That's what Microsoft is building. Yeah.
It's not impervious to tunnel, so like you have.
Very good. If you calculate the amplitudes of the top tunneling, it drops exponentially with distance.
Like if you're considering an outside system.
Remember, the tunneling depended on how high the wall was and how wide it was. The tunnel is very wide, but the term tunneling is inappropriate here, but there is an analogous statement that applies to what you said. Yeah, so it's another question. Yeah.
Does this mean you have to have like a coherent or state that spans all the way from one of these particles?
No, that's the point. No, that's the beauty of quantum topological quantum computing. No, the answer to that is no, but let's talk about this later. Thank you so much, guys. Somebody left the jacket in my office, so please come by and pick it up.
Except 0, 0.
Yeah, it's depending on where I click it.